the ratio test. If the limit at n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is equal to L, is mean it convert to a number, and this number is less than 1, then the series is absolutely convergent and therefore convergent. If this limit is greater than 1 or infinity, then the series is divergent. If the limit then equal to 1, the ratio test is being inconclusive. What does it mean by being inconclusive? It meant that we don't know what conclusion to be drawn about the series. This meant you need to move on to try a different test. So here, I want to take a look at the proof for this ratio test is provided to you in our books, and you should have the access to the book via the Canvas page. If you don't, let me know. So go take a look at the proof yourself. It's pretty intuitive. And I'm more than happy to help you with the proof along if you would just let me know. Okay. So let's take a look at a couple of examples, see how do we use the ratio test. So let's test the ratio for convergence. So here we are given this series of -1 to the n times n to the third divided by 3 to the n. Okay. So here we can see that a sub n is equal to -1 to the n times n to the third divided by 3 to the n. Okay. A sub n plus 1 is equal -1 to the n plus 1 times n plus 1 to the third divided by 3 to the n plus 1. So let's take a look at the limit. The limit as n approaches infinity of absolute value of a sub n plus 1 divided by a sub n. But when we take the absolute value, the negative term go away. So I will just take a look at the positive term. n plus 1 to the third divided by 3 to the n plus 1. Divide by a sub n. Well, divide and multiply with the reciprocal. I'll go ahead and simplify this. So this meant I'm looking at the limit that n approaches infinity, that 1/3 times n plus 1 divided by n to the third. Limit at n approaches infinity, that 1/3 times 1 plus 1 over n to the third. So this is equal to 1/3 less than 1. Then I conclude that the series n equal 1 to infinity of -1 to infinity n to the third 3 to the n. This is converged by the ratio test. And this is absolutely converged. Now let's take a look at the next one. I have 2 to the n divided by n factorial. Again, a sub n equal 2 to the n divided by n factorial. A sub n plus 1 equal 2 to the n plus 1 divided by n plus 1 factorial. Then the limit at n approaches infinity of the absolute value of a sub n plus 1. So in this case, both terms, these are increasing terms and they're all positive. So I'll drop the absolute value. 2 to the n plus 1 divided by n plus 1 factorial, multiply with the reciprocal, n plus 1 divided by 2 to the n. Well, n plus 1 factorial is equal to n factorial times n plus 1. So that's simplified out here. So then here I get 2 divided by n plus 1. As n approaches infinity, this approaches 0. And this is, according to our test, it is still less than 1. This means this series is absolutely converged. Therefore, convergent. Okay. Take a look at the next thing that we want to cover, the root test. If the limit at n approaches infinity of the n root of a sub n equal L is less than 1, then the series is absolutely convergent and therefore convergent. If L is greater than 1 or equal to infinity, then the series divergent. If it's equal to 1, then the root test is inconclusive. So test for the convergence of the series. So let's take a look at the limit at n approaches infinity of n root of the absolute value of 2n plus 3 divided by 3n plus 2 to the n. This equals the limit at n approaches infinity of 2 to the n plus 3 divided by 3n plus 2. This equals 2/3, less than 1. So our series is absolutely convergent. And therefore converge. In the next case, we have root of ln. We have n to the n divided by ln of n to the exponent n. Okay, so and the start at n equal 2. So let's go ahead and calculate this limit. The limit at n approaches infinity of the n root of the absolute value of n divided by ln of n. The n root cancel out. So this is just the limit at n approaches infinity of n divided by ln of n. And we use L'Hospital rule here. The limit at n approaches infinity, derivative of n equal 1 derivative of Ln of n equal 1 over n equal infinity. So then the series is divergent. So we have gone over several tests for convergent and divergent. So how do we know when to use which test? Okay. So let's take a look at, here's your book. Here's some strategy for solving for convergent, for choosing a convergent or divergent test for a series. We follow the step below. Okay. We start with, is it a familiar series? Is it a harmonic series, which is diverged, or the alternating series, harmonic series, which is converged? Is it a P series or geometric series? If so, check for the power P or the ratio R to determine if the series converge. The next thing is it an alternating series? If it's alternating, we're interested in absolute convergence or just convergent. If we are just interested in whether the series converge, apply the alternate series test. If we're interested in the absolute convergence, we proceed to the next step, considering the series of the absolute value. The next step, is it similar to a P series or geometric series? If so, try the comparison test or the limit comparison test. Do the term contain a factorial or power? If the term are powers such that a sub b equal b, a sub n equal b to the sub n to the exponent n, then we try the root test. Otherwise, we try the ratio test first. Use the divergent test if the test does not provide any information, or we can try the integral test. Yeah. So here we have a table of the test. I would suggest you to print out this table. You can use this table on your test, and I will have this table attached with your test as well.